Hi everybody. The purpose of this video is to go over section 2 of chapter 4, and here we're going to talk about exponential functions. Specifically, we're going to talk about exponential functions, exponential equations, compound interest, loans, and investments, and we are going to conclude with the discussion of Euler's number, the dreaded number E. So what is a exponential function? Well, this is an exponential function. It is f of x is equal to a raised to the x power. Of course, we do have some restrictions on a. First, it has to be a real number. Secondly, it has to be strictly positive. And thirdly, it cannot be equal to 1. Why? Well, if a was equal to 1, then you would have that f of x is equal to 1 raised to the x power, which would just simply be 1. Not very interesting. One of the things that we are going to need to do is to evaluate exponential functions for certain values of x. So here, in this example, we're going to set f of x is equal to 4 of x, and we're going to evaluate 4 raised to the x power for different values of x. The first one is f evaluated negative 2. This will be equal to 4 to the negative 2 power. We can rewrite this as 1 over 4 squared. And of course, 4 squared is 16, so this will be 1 over 16, and we are good to go. Okay, the next one is f evaluated when x is equal to 5, and that will be equal to 4 to the 5th power. Now, if you've done a lot of work in computer science, or you've done a lot of work in digital signal processing and all sorts of fun stuff like that, you may be very familiar with powers of 2, and it turns out that we can rewrite this as 2 squared, all raised to the 5th power, and that of course is 2 to the 10th. And once again, if you're in those aforementioned disciplines, then you will probably immediately realize that this is equal to 1024, which is also what we call in the digital signal processing world, we call this 1K. Okay. Next, we have f evaluated at 2/3, and this, of course, would be 4 evaluated at the rational exponent 2/3. And there's a couple of ways that we can actually do this. The first way is we can try to compute 4 to the 1/3 power, and then square that. Probably not the best way to go, since I have no idea what 4 to the 1/3 power is. Another way to go might be 4 squared, and then raise that to the 1/3 power. And that is the way that I'm going to go. Why? Because I know that 4 squared is 16. And I can raise that to the 1/3 power. Okay, I know I can rewrite 16 as 2 times 8. And I also know that 2 times 8 is actually 2 cubed. So this will give me 2 to the 1/3 power times 2 cubed to the 1/3 power. Of course, 2 cubed to the 1/3 power is just 2, and that leaves me with 2 times 2 to the 1/3 power. Now the next one is 4 raised to the 2.15 power. And really the only decent way to compute that is with a calculator. So here is my handy dandy Windows calculator. So what I'm going to do is I'm going to click on 4. I'm going to click on the power button right here. And then I'm going to click on 2.15. And this gives me 4 to the 2.15 power. And the answer to that will be 19.6983 and so on. Now typically ML is going to want you to provide that answer probably down with the accuracy, with the precision down to the hundredths place. So it might be best when you write this down to write it down to the thousandth, which would be 19.698, and then using the thousandth digit, we can use that to round this to the nearest hundredth. Okay, and since this is greater than 5, we will actually want to round up, and that will give us 19.70. Okay, and there we go. Now, let's talk about exponential functions. And this right here is the graph of f of x is equal to a raised to the x power for the case when a is strictly greater than 1. Okay, and here we go. A couple of things you can notice about this thing is that the domain for this function will be the entire real line. However, this function never takes on negative values and it never reaches 0, although it can become arbitrarily close to 0. As a consequence, their range is from 0 to infinity. Furthermore, we can see that this function is increasing. It is always going up. It is never constant and never changes direction. So it is increasing and it is continuous. And since it's always increasing and never changes direction, it is a one-to-one function. Also notice that as x approaches negative infinity, the function approaches 0 but never quite reaches it. As a consequence, the x-axis is a horizontal asymptote. And then finally, the graph goes through the points -1, 1 over a, which I forgot to plot. There it is. 0, 1, and then 1, a. Those are the 3 critical points on the graph. And one thing that you'll notice for the case when a is less than 1 is that the graph tends to begin to reflect a little bit. Okay, and so here we have the graph of f of x for the case where a is between 0 and 1. So once again, this is f of x is equal to a raised to the x power. However, now a is less than 1. Okay, the domain is still the same. It still takes on strictly positive values, but now instead of increasing for all values on the domain, it is now decreasing for all values in the domain. It is still continuous, but since it's always increasing, or in this case, since it's always decreasing, it is a one-to-one function. Once again, as x approaches infinity, the function approaches 0 but never quite reaches it. So the x-axis is a horizontal asymptote. And then finally, the graph passes through the points -1, 1 over a, which in this case is a number greater than 1, 0, 1, and then a 1, a, which of course is a negative number since now a is less than 1. So we can use this information about graphs to actually either plot or in our case evaluate different candidates for the graph of a certain function. And here, in this example, you are encouraged to graph y is equal to 1/5 raised to the x power on paper and then to choose the correct graph. Okay, well, let's go ahead and I would encourage you to do this. It's a good practice, but in MML you are going to be given a number of options and you have to choose the correct option. Now, these three, this one right here, takes on negative values, and this takes on negative values, as does this. So none of these are contenders. Actually, this right here is y is equal to y is equal to x to the 1/5 power. I forgot what these are. Okay, this one is the only one that fits all the criteria for an exponential function when y is less than 1. It's decreasing. It approaches 0 as x approaches infinity. Moreover, when x is equal to -1, y is equal to 5. And when x is equal to 1, y is equal to 1/5. And of course, it crosses at 1, 1. So this is the correct graph. Now take a look at this one. This is y is equal to 5/4 raised to the x power. Of course, 5/4 is greater than 1. As a consequence, our graph should be increasing. Okay? Furthermore, since this is an exponential function, it cannot take on negative values. So this cannot be the graph, and this cannot be the graph. Now, the domain of this particular graph is all positive or all non-negative real numbers. And the domain for our exponential function should take on the entire real line. So this can't be out. So this must be the graph of interest. And is it? Well, it crosses the y-axis at y equals 1, so that's good. It takes on the value of 1 1/4 when x is equal to 1, and it takes on the value of 0.8 when x is equal to -1, so this one actually works. Okay, now we want to go ahead and talk a little bit about transformations of exponential functions. And the transformations that we are going to be looking at are reflections about y and also transformations or translations. Okay, now take a look. This is f of x and it's equal to a of x, and it's equal to a raised to the x power, and g of x is equal to 1 over a raised to the x power. Now g of x we can rewrite as a raised to the negative first power, all that raised to the x power. And then using our product rule, we have that g of x is equal to a raised to the negative x power, which is basically nothing more than f evaluated at negative x. So as a consequence, g of x, since g of x equals f of negative x, well, that's the definition for a reflection across the y-axis, and that is indeed what we have. Now, we could also have a reflection across the x-axis, and that would occur if g of x is equal to negative f of x, or if we had another function, h of x, which is equal to negative f of x. That would be a reflection across the x-axis. Okay, so let's actually use that information for our next example. And here we have the function f of x is equal to 1/4 to the negative x power. Okay, so we can write 1/4 as 4 to the negative 1. And we're going to raise all of that to the x power, to the negative x power, I apologize. And then using the power rule, this is going to be equal to 4 times negative 1, not I, times negative x, which will be 4 to the x power. So the plot of f of x is going to be the plot of 4 to the x power. All right, since a is greater than 1, our plot is always going to be increasing. So this one is out, this one actually right, and this one is out, and this one is out. Okay, also, since the range is all positive values of x, this one has to be out. And so we're left with this one right here, and this actually is indeed our plot of f of x. Now this one is the plot of its reflection. This is actually the plot of, let's go ahead and call it g, of 1/4 raised to the x power. As a consequence, this over here is the plot of negative g of x, and this, which is a reflection of g across the x-axis, and this is a plot of negative f of x. But to answer the question, this is the plot of our given function. We'll also be looking at translations. So take a look at this function. Here we have f of x, which is equal to 4 raised to the x plus 5 power, and all that's going to be subtracted by 3. So notice that our base function is going to be 4 raised to the x power. So the base function, I guess I can call it b of x, is equal to 4 to the x power. Okay, so what translations do we need to actually plot this particular function? Well, we want to start with our base function, and then since we are doing x plus 5, that implies a right shift, that implies a left shift, my apologies, of 5 units. And then the negative 3 implies a downshift of 3 units. Well, does this work? Well, let's find out. Now, if you've noticed, every single exponential function, or at least base function, always passes to the point 0, 1. You can almost call that an anchor point. Okay, so what would happen if we shifted by if we shifted by 5? We go 1, 2, 3, 4, 5, and then shifted down by 1, and then shifted down by 3. 1, 2, 3. We get right here. Okay, kind of notice this is our shifted down asymptote, and if we go up and if we go up by 1, we are right here. Okay, so that sort of makes sense. Furthermore, if the base function is 4x, then when x is equal to 1, y is going to be equal to 4, which is somewhere off the screen over here. So if I shifted to the left by 5, 1, 2, 3, 4, 5, and then down by 3, I should end up at 1. 1, 2, 3, and there I am. Okay, and then similarly at -1, I should be at a quarter, which is right about 1, 2, right about there. So if I went 5, that would bring me down to here. No, down to here, my apologies. And then if I went down 3, 1, 1, 2, 3, that would put me right about there. So this actually does indeed work out. Now, what is the domain of f? Well, the domain has not changed. It is still the entire real line. However, what has changed is the range. Since we are shifting down by 3, instead of the range going from 0 to infinity, it now goes from -3, not including -3, all the way to infinity. And there you go. And this means that we can talk about solving exponential functions. And the tool that we're going to use is this property right here for exponents. And that is if two expressions have the exact same base, then their exponents have to be equal. So if a raised to the b power equals a raised to the c power, then b equals c. And this if and only statement tells us that if b is equal to c, then a raised to the b power is equal to a raised to the c power. And if a raised to the c power is equal to a raised to the b power, well, then that implies that c is equal to b. And that's what we're going to use. So how are we going to use this property to solve these two problems? We're going to try to express both terms using a common base. So what we can do here is express 1/5 as 5 to the -1 power raised to the x power. And then we can express 625 as 5 raised to the 4th power. Okay, are we there? Not quite, because we need to get rid of this, deal with this exponent, and we can use the power rule, and that will give us that 5 to the -x power is equal to 5 to the 4th power. Now we have common bases, and that will imply that -x is equal to 4. Solving for x, we have x is equal to 4, and that would be our solution to this equation. We're going to use the exact same approach here. We're going to express both of these as a common base, and once we do, then we can actually set the corresponding exponents equal. Now notice that we can write 9 as 3 squared, so then that will give us 3 to the x plus 1 power is going to be equal to 3 squared, all that raised to the x minus 3 power. All right, we can go ahead and use the product rule, and if we do, we will have basically the exact same thing over there. 3 raised to the x plus 1 power. But on the right-hand side, we'll have 3 raised to the 2x minus 6 power. And here we go. Same basis, and that means that the exponents would be equal, and that would specifically that would imply that x plus 1 is equal to 2x minus 6. We can actually subtract x from both sides, and that will give us 1 is equal to x minus 6. We can add 6 to both sides, and we will have our desired solution. X is equal to 7. Okay, well, what about something like this? Well, notice that if I raised x to the 2/3 to the reciprocal of 2/3, which would be 3/2, then using the power rule, I will have that this is equal to x to the 2/3 times 3/2, which is equal to x to the 1, or just simply x. Okay, so that basically means that x is going to be equal to 25 raised to the 3/2 power. However, notice that I have a even value in the denominator of the exponent. That also means that I need to consider x, evaluate the equation x is equal to negative 25 raised to the 3/2 power. Okay? So let's go ahead and evaluate both. The best way to do this would be to first take the square root. And then cube it. And if I do, I will have negative 5 cubed, which will be negative 125. Doing the exact same thing over here, I will have positive 125. Does it work? Well, let's do the negative one first. Here we are going to have negative 125 raised to the 2/3 power. I can rewrite that as negative 125 to the 1/3 power, all of this squared. Okay, well, negative 125 to the 1/3 power is negative 5. So this is going to be negative 5, the entire thing squared, and that will be equal to 25, which is our desired result. And we'll get the same result if we actually evaluated this with 125. So for this one, we can just basically get we can isolate x by raising this to the reciprocal power. However, if the denominator happens to be even, like this one is right here, then we need to consider both positive and negative values. Okay, and this brings us to the one application that we want to talk about, which is compound interest, which is the financial tool that most homeowners and car owners are familiar with. Now, actually, most car owners and homeowners, they either have a car loan or a mortgage, and that actually is not a compound interest loan. It is actually something called an annuity, where you actually make periodic constant payments, typically monthly. However, the annuity, which actually has a more involved formula, is based in part on the compound interest formula. And this is the formula right here. Here we have A. A is the future value of the loan or the investment. So if it's an investment, it is the amount that you will get. It is the amount that you will get after a certain period of time. Okay, and this is going to be equal to P, which is the amount that you would put into, which is the present value of the loan or the investment. So if it is an investment, this is the amount that you would put in, okay, and then at a certain time later you will receive A. If it's a loan, this will be the amount that you receive, and then a certain time later you will have to pay back A. Okay. R is the annual interest rate, but it needs to be expressed as a decimal. So if they give you an interest rate of 2.8%, then R is going to be that divided by 100, or 0.028. N is the number of compounding payments per year. So if it's quarterly, it is 4 payments per year. If it's monthly, it is 12. If it is weekly, it is 32. No, 52, not 32. And if it's semi-annually, it is just simply 2. And then T is the duration of the loan, and it will always be in years. Okay, so how do we use this sucker? Well, in this particular problem, Brandon has to come up with $15,000 in 8 years. Okay, and he has access to an account an investment account that will pay him an annual rate of 4.8%, and it's going to be compounded quarterly. And the question is, how much would he need to put in now so that in 8 years, or 32 quarterly payments, he will have $15,000. So in this particular case, A is $15,000. Okay, your interest rate is 4.8%, so R is going to be that divided by 100, or 0.048. The duration of the loan is 8 years. You're being paid quarterly, or your investment is being compounded quarterly. So that means that N is going to be equal to 4. Now, normally you would need to compute what NT is, but they already gave it to you. It's 32. So our formula is A will be equal to P times the quantity 1 plus r over n raised to the nt power. So we can go ahead and do our substitutions. One is we know that A is $15,000. That's going to be equal to P, and we don't know what that is yet. But that's going to be equal to 1 plus our interest rate, which is 0.048, divided by the number of payments, which is going to be 4 per year, and all that's going to be raised to the 32nd power. Now we can do some simplification. For example, 0.048 divided by 4 is going to be 0.012. So that will give us P times 1.012 raised to the 32nd power. Okay, so let me just go ahead and clean that up a little bit. That means that now we have 15,000 is going to be equal to P times 1.012 raised to the 15th power. No, I'm sorry, raised to the 32nd power. Okay, since we're solving for P, we can rewrite this as P is equal to 15,000 divided by 1.012 raised to the 32nd power. And when you do that math, you will find that P is equal to $10,240 and 35 cents. Okay, great. That is our answer. Now, well, how much interest did he earn? Well, that will be the difference between the amount he received, which is A, minus the amount that he put in, which is P. All right, he received $15,000. He put in $10,240.35, not 36 cents. And that will come out to $4,759.65. I'm getting my cents backed up, messed up, which, makes no sense. Okay, and that is that particular problem. Now, one of the problems you're going to have in your homework is this. Here we have 3 banks. Okay, one bank lends money at 7.25% and is compounded quarterly. The other one charges a higher interest rate of 7.3%, but is only compounded annually. And then the third bank is lending money at 7.2% and is compounded monthly. And which bank will pay you the least interest? Well, let's go ahead and look at a particular case. Suppose that in any particular case you are going to invest, or you're going to want to borrow P dollars, okay, and you want to pay it back after a period of T years. So we want to keep this constant through all the banks. So the things that are going to vary will be the amount you have to pay back, obviously, the interest rate, and then the compounding period. Okay, so the amount that you'll have to pay back a particular bank, I'm going to call that A sub I, is going to be equal to the amount you borrow, which is P, that's going to be fixed, times 1 plus your interest rate for that bank, the type of compounding for that bank, so R sub I over N sub I, raised to the N sub I T. Now I can play with this a little bit, and I can write this as P times the quantity 1 plus R sub I divided by N sub I raised to the M sub ith power times T. Okay, so my banks are going to be A, B, and C, and the only thing that will change in this equation between the 3 banks is this value right here. The larger this value, the more that I have to pay. P will stay the same, T will stay the same. So to compare, to determine which bank pays the least interest, all I really need to do is compute this quantity and figure out which bank provides me the smallest quantity. So let's go ahead and do that. For bank A, we have the interest rate is 7.25% or 0.0725. Let me fix that 0 right there. And it's going to be compounded quarterly, so N is equal to 4. All right, well, that's going to give me 1 plus 0.0725 divided by 4, all raised to the 4th power. And if I do that math, I will have 1.074495. Okay, now for bank B, I would have 1 plus 0.073 divided by 1 raised to the 1st power, which really is nothing more than 1.073. That's bank B. Now for bank C, I will have 1 plus 0.72. No, that's not it. I will have 1 plus 0.072 divided by 12 raised to the 12th power. Okay, and if I do that math, I will have 1.0744424. So this is C, this is B, and this is A. We have 1.74, 1.074, 1.074, and here is 1.073. This right here is the smallest. So it turns out that bank B, the one that has the highest interest rate but is only compounded annually, will provide me the least interest. Okay, now the last thing that we want to talk about today, or at least that I want to talk about today, is Euler's number, the number E. Now, this number is very useful in mathematics. You'll find it amazingly useful if you ever take calculus, because the derivatives and integrals are a piece of cake. And it's also because it's very useful, it's used as a modeling tool, or e to the x is used as a modeling tool for many, many applications. Well, the first thing I want to mention is if you were actually had a compound interest problem where the interest rate was 1, it turns out that your expression would come down to about this, and as n goes to infinity, in other words, as you compound more and more and more often, it turns out this value approaches this magical number E. The other cool thing about this number is that if you actually took the reciprocal function, and if you wanted to know, how far out you had to go until the area under the curve is equal to 1, well, you have to go all the way out to x is equal to E, and then the area under the curve 1 over x from 1 to E is actually 1. It also turns out that E is the base for the natural logarithm. The base for the natural logarithm is E. As a consequence, the natural log of E is equal to 1. Just like the base for the common log is 10, and the common log of 10 is equal to 1. So that is all that I have for this particular section. If you have any questions, please feel free to contact me. This is Bob Boyle, signing off.